In this video, we take a closer look at the stresses that occur in the belt of a belt drive and the resulting consequences for the optimum belt speed. This is important because the total stress must not exceed certain limits, otherwise the belt may become unacceptably deformed or even break. The permissible stresses depend on the belt material and can be found in the belt manufacturer's datasheets. Let us first look at the forces that actually occur in a belt. On the one hand, there are the quasi-static belt forces relevant to the actual power transmission in the form of the tight side force Ft and the slack side force Fs. More information on these belt forces can be found in the linked video on the basics of a belt drive. At high belt speeds, additional centrifugal forces act to pull the belt outwards. This creates an additional centrifugal belt force on both the tight side and the slack side of the belt. More information on this can be found in the linked video. If these forces are related to the cross-sectional area S of the belt, we obtain the stresses caused by the respective forces. These are referred to as the tight side stress sigma T, the slack side stress sigma S, and the centrifugal stress sigma F. To calculate the centrifugal force, we can use the formula from the linked video on centrifugal belt force. In this formula, M' is the specific weight of the belt, which is the belt mass per unit belt length, and V is the belt speed. When this specific weight is used in the formula for the centrifugal force of the belt, the product of the belt length L and the cross-sectional area S in the denominator can be interpreted as the belt volume V. The quotient of the belt mass M and the belt volume V now corresponds to the density of the belt rho. The centrifugal stress is therefore simply the product of the belt density and the square of the belt speed. Typical values for the density of belt materials are in the range of 0.8 to 1.5 grams per cubic centimeter. The maximum belt speeds range around 30 to 120 meters per second. In addition to the stresses already mentioned, bending stresses must also be taken into account, which occur when the belt runs around the pulleys and is bent over the pulley. This stretches the belt at the outer edges and compresses it at the inner edges. In between is the neutral axis, which is neither stretched nor compressed and therefore does not experience any stress. The elongations and compressions result in tensile stresses in the outer belt area and compressive stresses in the inner belt area. The tensile stresses are critical because they act as a pulling force in addition to the tight or slack side force and the centrifugal force. The tensile stresses caused by bending increase outwards, starting from the neutral axis, and are maximum at the surface of the belt. This maximum stress is then referred to as the bending stress sigma B. The more the belt is bent, which means the smaller the pulley, and the thicker the belt, the greater the bending stresses. According to linear elastic bending theory, the bending stress sigma B can be determined for a given bending diameter d, which we equate here to the pulley diameter, and a given belt thickness S using the so-called flexural modulus or bending modulus EB of the belt material. The flexural modulus for standard belt materials is typically in the range of 30 to 100 newtons per square millimeter, but can also be significantly higher. Please note that the illustration of the flat belt in this video is not to scale. Especially for flat belts, the belt thickness is significantly less than the pulley diameter. The pulley diameter is typically 50 to 100 times larger than the belt thickness. For this reason, the belt thickness S can often be neglected compared to the pulley diameter d. In these cases, the formula can be simplified as shown, and the actual bending stresses will be lower than the calculated ones. We can now see that the bending stress is directly related to the ratio of belt thickness to pulley diameter. This means that the smaller the pulley diameter and the greater the belt thickness, the greater the bending stress. Therefore, the maximum bending stress occurs when the belt runs around the smaller of the two pulleys. This is usually the drive pulley. So note, the maximum bending stresses occur when the belt runs around the smaller of the two pulleys. The different stresses in the belt are now to be plotted graphically. This is done by plotting the stresses perpendicular to the belt. Let's start with the power transmitting components in the form of the tight side stress and the slack side stress. Note that the belt stress increases around the output pulley and decreases around the input pulley. The difference between the two stresses corresponds to the force transmitting stress sigma C, with which the circumferential force Fc is ultimately transmitted. This can be easily seen by relating the transmitted circumferential force Fc to the cross-sectional area S of the belt. As explained in detail in the video on the basics of power transmission, the circumferential force is the difference between the tight side force Ft and the slack side force Fs. As we can now see, the force transmitting stress is the difference between the tight side stress and the slack side stress. In addition to these force transmitting stresses, the belt also experiences centrifugal stress at high belt speeds. This stress is constant along the entire belt and therefore acts equally at each point. Bending stresses must also be considered. These only act as the belt rotates around the pulleys, with the maximum bending stress occurring on the smaller pulley. This results in the illustrated stress distribution along the belt. It can now be seen that the maximum belt stress occurs on the tight side of the belt, where the belt runs on the drive pulley. The maximum belt stress sigma max is therefore the sum of the tight side stress sigma T, the centrifugal stress sigma F, and the bending stress sigma B. This maximum stress is the basis for dimensioning the belt. It must always be ensured that the maximum permissible belt stress is not exceeded. Allowable belt stresses typically range from 5 to 50 newtons per square millimeter, but can also be significantly higher. Bending occurs in the belt every time it rotates around a pulley. It does not matter if it is a drive pulley, driven pulley, idler pulley, guide pulley, or tensioner pulley. The belt will bend each time it passes around such pulleys. This bending requires a certain amount of energy. The smaller the diameter of the pulley, the more energy is required to bend the belt. The work required to bend the belt not only reduces efficiency, but also causes very high mechanical and thermal stress on the belt. The more often a belt bends per unit time, which means the higher its bending frequency Fb, the shorter its service life. Therefore, depending on the type and manufacturer, the belt must not exceed a certain permissible bending frequency in addition to the maximum permissible bending stress. The bending frequency Fb is calculated from the belt length L, the belt speed V, and the number Z of pulleys or rollers. Typical values for the maximum permissible bending frequencies are in the range between 50 and 100 Hz. The power transmitted by the belt will be examined in more detail in the following. The transmitted power results from the product of the circumferential force Fc and the circumferential speed, which in this case corresponds to the belt speed V. If we neglect the elastic slip and frictional influences, this power is transmitted from the input pulley to the belt, which then transmits the power to the output pulley without any losses. However, it turns out that the belt cannot transmit any power due to its limited strength, and that there is even an optimum belt speed at which the maximum power can be transmitted. This will be explained in more detail in the following. First, the influence of the belt speed on the power should be examined in more detail. According to the formula, the transmitted power increases with increasing belt speed. However, the belt speed cannot be increased at will, as the centrifugal forces rise sharply with increasing speed. As a result, the maximum permissible stress is exceeded at some point and the belt tears. Since the stress in the tight side is limited by the strength of the belt, the increase in centrifugal stress is at the expense of the maximum permissible tight side stress. This becomes immediately clear when we solve the formula for the maximum belt stress with respect to the tight side stress sigma T. If we use the maximum allowable stress as the maximum belt stress, this formula gives us the maximum permissible tight side stress for a given centrifugal stress. The centrifugal stress is expressed by the product of belt density ρ and belt speed V. This means that the maximum permissible tight side stress is directly dependent on the belt speed. You can see immediately that the maximum allowable tight side stress decreases as the belt speed increases. However, this is also directly related to a decrease in the maximum transmittable circumferential force, as we will see in a moment. This is because, as already explained in the video on the basics of power transmission, the maximum transmittable circumferential force can be determined as shown for a given tight side force, which in this case corresponds to the maximum permissible tight side force. For simplicity, we will refer to the term in brackets, which includes the wrap angle phi and the coefficient of friction mu, as the yield factor K. At this point, we express the maximum permissible tight side force as the product of the maximum permissible tight side stress and the cross-sectional area of the belt. We express the maximum permissible tight side stress using the formula already derived and obtain the shown formula for calculating the maximum transmittable circumferential force as a function of the belt speed. The decrease of the maximum transmittable circumferential force with increasing belt speed can be seen immediately. In extreme cases, at very high speeds, the centrifugal forces are so great that no circumferential force, and therefore no power, can be transmitted because the permissible belt stress would immediately be exceeded. Excessively high belt speeds can therefore no longer be used to transmit high power. So note, increasing the belt speed will reduce the maximum transmittable circumferential force, as otherwise the centrifugal force would place an unacceptably high load on the belt. The transmittable power will therefore decrease at very high belt speeds. On the other hand, although high circumferential forces can be transmitted at low belt speeds, the transmitted power is low because there are no high belt speeds. Therefore, there is an optimum belt speed, which is a compromise between a high belt speed and a sufficiently high circumferential force at which the maximum possible power is transmitted. This will be discussed in more detail in the following. To determine this optimum belt speed, we first determine the formula for the maximum transmittable power as a function of the belt speed. To do this, we use the maximum circumferential force Fcmax in the formula for the transmitted power and thus obtain the maximum transmittable power Pmax at a given speed v. We express the maximum circumferential force using the formula already derived. Now we express the cross-sectional area of the flat belt by its belt thickness S and its belt width B. We then obtain the shown formula for the maximum transmittable power Pmax as a function of the belt speed v. It should be noted that for the yield factor K, the smallest wrap angle that occurs is decisive. As a rule, this is at the smallest pulley, especially as this is where the greatest bending stresses occur. Both the wrap angle phi, relevant for the yield factor, and the pulley diameter d, relevant for the bending stress, therefore refer to the smallest of the existing pulleys. Power Pmax is often not given as an absolute value, but related to the belt width b and given as a so-called specific power, which means the power per unit belt width. This makes sense because the belt thickness S has to be taken as given anyway for the calculation of the bending stress sigma b. This leaves the belt width b as the only unknown geometric quantity. Therefore, it makes sense to first express the power independent of the belt width and to specify it as a specific power. In practice, the belt width be required to transmit the nominal power Pn is then calculated from this maximum transmittable specific power. For safety reasons, various operating factors C are also taken into account, which include the influence of shock-like torque loads and various environmental influences that can lead to a reduction in friction. The diagram shows the maximum transmittable specific power Pmax for the given values as a function of the belt speed v according to the equation derived. It is now also graphically clear that neither too low nor too high belt speeds lead to arbitrarily high transferable power. There is a distinct maximum in which the maximum possible power can be transmitted. To the left of the peak, the drop in power is due to the decreasing speed. To the right of the peak, the decrease in power is due to the high centrifugal forces, which lead to lower transmittable circumferential forces. If you want to transfer as much power as possible with a belt drive, the belt speed must be adjusted to achieve the optimum power. This is called the optimum belt speed. In this case, it is approximately 50 meters per second, which corresponds to a pulley speed of approximately 4,800 revolutions per minute. As this example shows, optimum belt speeds are often very high and are usually not achieved in practice. To calculate the optimum belt speed, the maximum value of the function Pmax must be found. Mathematically, this corresponds to equating the first derivative of the corresponding function with 0. After solving this equation, the shown formula for calculating the optimum belt speed is obtained. For a given transmission ratio and rotational speed of the drive pulley, the belt speed can be adjusted by using larger or smaller pulleys so that the optimum speed is achieved. However, in order to maintain the desired transmission ratio, both pulleys must always be changed to the same extent. Please note that changing the pulley diameter also changes the bending stress and therefore the optimum belt speed. The maximum specific power, or the maximum power that is transmitted at the optimum belt speed, is then obtained by using the formula for the optimum belt speed in the corresponding power formulas.